we're going to take a look at two examples of being able to evaluate integrals, but this time we're going to be using geometry instead of left hand and right hand being in sum rules. So the first one that we have is the absolute value of x plus 1, and we're trying to figure out what the area is from -2 to 3. All right, so first thing we're going to do is we're going to graph this. All right, so if we graph this function, in fact, let me make that a little bit bigger because we really do need to be pretty accurate when we graph this thing. When we substitute 3 back in for the function, that just gives us the absolute value of 4, which is 4. Okay, so one of the points that's going to be on this function is going to be 1, 2, 3, and 1, 2, 3, 4. All right, so we have this point. We know that when x equals -1, that there's going to be a 0, or it's going to be touching. All right, so it's going to look something like this, at least this side. Right, and then finally, when x is -2, then we have our y value of 1. All right, because it'll be -2 plus 1 absolute value. All right, so what we're looking at is we're looking at this area, and we're also looking at this area. Okay, so now that we have that, we're going to just use the sketches of the graphs, and we're going to find the area of each of these. All right, so the good news is we know that these are both triangles, and the area of a triangle is 1/2 base times height. All right, so we know that the base of this triangle is 1. We know that the height of that triangle is 1. All right, so if I call this area 1, that's going to be 1/2 times 1 times 1, or 1/2. Now I'm going to hold on to that because I need to figure out what's the area of this second triangle. So we know that the height of this triangle is 4. Okay, and again, that's just because we know that this is the point 3, 4. Right? We know that this is the point -1, 0. Okay, and we also know that this is the point 3, 0 on the graph. All right, so we know that the length is 1, 2, 3, 4, or the base is 4. All right, so it actually winds up being a triangle with 2 sides that are going to be the same. So the area 2 is going to be 1/2 times 4 times 4, or 8. Okay, now the total area is going to be A1 plus A2, which is 1/2 plus 8, which is going to wind up being 16/2 plus 1/2, which is going to be 17/2. All right, now that is the precise value of this integral. All right, and it's a little bit easier than using the right hand and left hand rule, but again, when we're doing this, we're doing geometry, and not every sort of function is going to give us a really nice geometric shape. Okay, so we have to be cognizant of that fact. All right, a second example is we have 4 minus x squared on square root of that, and we're binding it from -2 to 2. All right, so now if I want to graph that, and if I don't know what a graph of it looks like, I can use foo plot. All right, so I'm just going to go ahead and use my foo plot. Still have the cosine function, and we have the square root of 4 minus x squared. All right. And we want that to go from -2 to +2. All right, so now, although we can't see it really well, if I was to zoom out a little bit with this, it actually winds up being a circle. All right, and I know it's difficult to see. It looks more elliptical, but truly, if it's -2 to +2 and 2, we could probably get like some sort of circular. So if I make this a complete box, then we might be able to see it's more circular. Okay, so the good news is that the graph of this is just going to be a circle. Right, so if I sketch it, and it's going to be the top part of that circle, excuse me, it's going to be a semicircle. So this is -2, this is +2, this is the point 0, 2, not that it matters much, but we know that the radius of this semicircle is going to be 2. Okay, so we know that r is equal to 2 for this. And certainly we remember that the area is pi r squared. So the area for any circle is going to be pi r squared. In this case, 2 pi times 2 square, or 4 pi is the area. Okay, so there are a few times, and it's not many of them, but you can actually use the graph and the area bound by the graph to be able to evaluate an integral. Now, later we're going to see in the next series of videos that we don't necessarily need this sort of area to do this. We can use the fundamental theorem of calculus. But for right now, we're just going through and just showing you that you can use area to evaluate, get the exact values of some integrals.